Thank you. So this work is titled Limits of Recommendation. It's a joint work with Stefano Leucci, Alessandro Panconesi, Prabhakar Raghavan, Elisa Teroli. Okay, so let me give an introduction. So all of us are familiar with this kind of interface, right? Nowadays, you go on Amazon, and every time you bump into this system that tells you frequently bought together. So you bought this. I suggest you to buy also that item. Or you bump into the second case, right? Customers who bought this item also bought that other item. So this suggests to buy something that your friends, for example, people who are similar to you, bought previously. A similar case happens when you go on YouTube, right? You want to look at a Schumann concert piece for horns, and then you get flooded with recommendations of other videos that, according to YouTube, you should watch, because that's a good thing that would entertain you. So YouTube is trying to catch your attention to maximize its revenue in terms of advertising, for example, in this case. Or a third case can be that of reading books online. So there are platforms like this one that try to get you involved together with your friends, for example. You start reading books, you start telling the system which books you have read so far, and it tells you back, okay, listen, your best friend read that fantastic book. Why don't you read also that book? It will be good for you, right? So for all kinds of reasons, revenue, entertaining, and so on, recommender systems nowadays are everywhere, right? Wherever you buy something, do something online, you are suggested to take some action that, according to the system that is behind, is good for you and is good for the system. So that has massive economical implications, right? A huge amount of money is going around thanks to these systems. And so they have been studied thoroughly in terms of maximization of user experience, for example, of maximization of diversity of items suggested, of maximization of the profit from the companies. But today, we are interested in a different question. An intriguing question, which is the extent to which a market can be altered in the moment you put a recommender system into the market. So in the moment you start recommending items with respect to the old good days where you were just choosing items from the shop just on your own. So we would like to be able to answer in a quite precise way to questions like, will current bestsellers lose their status if a recommender system is introduced, for example? Will, vice versa, unknown products become hits? Will my sales of my product rise or fall? Will your purchasing behavior change under the effect of the recommender system, and so on? So we will need a model to answer these questions, and to start cutting down the possible scenarios. We focus on two key phenomena we want to capture with our model. The first one is the popularity effect, which has been documented since a long time ago. The simple fact that the more a product is bought, the more it becomes visible, and the more likely you will end up buying it, everything else being equal. And the second phenomenon is the role of social ties. So essentially, you tend to buy things that also your friend buy, right? Because either you ask them, because either they tell you, and this is often incorporated in many current recommender systems, ranging from YouTube to Amazon to the online bookshop I showed you before. All right, so we try to investigate with the first step into this field, and we develop a first mathematical model, a simple, minimal mathematical model, but that is able to capture quite a lot of things. So there are three key elements in the model. The first is the set of products in the market. So for example, think of the set of restaurants available in Venice, a set of users or buyers that are able to buy these products, and each user has a priori distribution over the products that reflect his own inclinations, his own personal inclinations. And then there is a graph that connects the users. It's a weighted directed graph, so no need for reciprocated arcs and arbitrary weights. And then we have a simple purchasing process, a stochastic process that goes on like this. In an infinite sequence of discrete time steps, a random user wakes up and then he buys a product as follows. Either with some probability 1 minus alpha, he chooses the product just according to his own preference distribution, or with probability alpha, it follows a recommendation from the recommender system. Then it buys the product, puts it in his list of purchases, and the process repeats. Okay, so how is a recommendation generated here? In the following simple way. Each time a user wants a recommendation, he looks at his neighbors, his incoming neighbors, picks one at random according to the weights of the arcs, and then asks him for a recommendation. At this point, the recommender looks at his past history of purchases and picks one item he purchased in the past according to some random distribution. And here, one crucial point is exactly the weight of history. So how the recommender chooses the product to recommend to the buyer, to the active buyer at time t. We want to allow for pretty much flexibility here. So what we do is to endorse the recommender node V with a set of weights over all his past purchases. So at time t, V has a set of weights for all the instances coming before t, and then he recommends the product that he has bought at the generic time I before t with a probability proportional to the weight placed over that time instant. So this is a very general setting, because that function can be whatever you like. Can change from time to time, can take different shape, and so on. So before moving to the analysis of this model, I want to convince you that this model is quite rich indeed. It's very simple, but it can capture a lot of situations. So for example, you can distinguish between markets where you can repeatedly buy the same items, like you listen to a song that you like many times a day, or you rewatch a movie, by just setting the set of products to be small, right? So the probability of drawing the same item is high. Conversely, if you set it to be large, you are modeling markets that where you seek for novelty, right? Which is one of the traditional trade-offs in recommender systems. The graph allows you to model a variety of situations according to recommendations. So for example, situations where recommendations come from friends can be modeled just by a social graph. If you want to model the users who bought these, also bought a kind of Amazon style, you can set G to reflect a similarity matrix between the users. If you want to capture just the plain popularity effect, you set G to be a click. If you want to model a centralized recommender system that affects everybody without being affected by the others, just set G to be a directed star from that super user. Incidentally, this model also captures the repeat consumption phenomenon, the fact that users tend to repeat their most recent purchases in time with a decaying patterns just by putting self-loops in the graph. So this captures also that situation. And the weight of history allows you to capture situations like scenarios like proper Christmas gift recommendations, right? So when you are under Christmas, you are less likely to recommend a product that you bought last August than one that you bought last December. So by modulating the H weight in a non-monotonic way, you can model also this scenario. All right, so now that we are convinced that this is a valid model, we can go to the main results. All right, so the question is now, where will this kind of market go? To make the question more precise, let's represent with x u of t the probability that if you buy something at time t, then he buys a given product p that we fix. We are observing a single given product. All the others we don't care about. All right. So if we capture everything, all these probabilities simultaneously for all users under a single vector, then we have a theorem that says that this kind of systems always converge to a unique steady state, and we have a closed form for this kind of steady state. And the only condition that determines the fact that it converges or not is if the past fades away. That is, if you ultimately, as the time goes on, you forget the purchases that you made back in time when you are recommending them, right? So ultimately, you won't recommend something that you bought an infinite amount of time ago, which is a very natural condition. If this holds, then the limit takes this simple form, which depends on two things: the structure of the directed graph with weights, and the vector describing the personal inclinations of users. So if the recommender system was not present here, what would happen? Each user would follow just the vector B, okay, where his BU gives the probability that he buys P, the product we are observing in time T. It will just be that. Now, when we introduce the recommender system, the limit behavior takes this form, this vector with this matricial expression. All right, so this already tells us something. This kind of system that encompasses a lot of scenarios always converge, but is also able to tell us more. In fact, the expression that you see that algebraic expression can be reformulated in the following way. So the steady state is nothing more than the personal inclination of users multiplied by a special matrix, okay, which has this form. And this is an influence matrix. So it maps the personal preference of users into the final market outcome for each user. So it's kind of, there's a kind of lot of information into this matrix. The generic element of this matrix indeed tells how much my personal inclinations go into your purchasing behavior at the limit. All right, this is what is it telling. A nice thing about this result is that you can actually compute all those things through standard linear algebra tools. So if you give me the initial state, if you give me the network, if you give me the probability of being contaminated by recommendations, and if you give me the personal inclination of users, I can tell you what the market will be at the end. All right. Yes? Excuse me? If it's too close to 1? It must be strictly less than 1. Actually, it is enough that at least one user has an alpha which is bounded away from 1, and this will converge. No, because there is there is an inversion of a matrix there. So it turns out that the rows of that matrix sum up to 1 minus 1 minus alpha. So that inverse matrix tends to explode when alpha is close to 1, and that term is compensating for that. You can prove that matrix is actually a stochastic matrix. Okay. So L is always well-defined. Rows sum to 1, whatever the alpha, as long as it is not 1. So, all right. So starting from this, we can tell a bunch of other interesting things. The first one is are measures of market distortion. So now I've talked about the basic model where each user wakes up at random at some point, but I haven't specified the frequency with which a user wakes up. You can attribute purchasing rate to each user, so each user wakes up at with a specific probability. And if you collect up these probabilities into a vector f, then what you obtain is that multiplying the matrix, the influence matrix L by this vector, you obtain an influence vector. So this tells for each user how much he affects the whole market at the end, right? So the higher his entry in this vector gamma, the higher his effects, his influence on the overall market. So a very influential user can be able to steer a significant fraction of the market sales at the limit. This is what this vector is telling us. So for example, by looking at the maximum value, which we'll do in the experiments of this vector over all users, we can determine how powerful is the most powerful user in the network. The second crucial measure we will look at is the market distortion. So the market distortion is simply how much the product has changed in overall sales thanks to the recommender system. So again, if the recommender system was not present, you will get just an overall market share equal to the vector of the purchasing rate times the probability distribution of the users. When the recommender system comes into play, things change and the overall market sales becomes proportional to gamma transposed times the personal preferences to the user. So this is just the limit behavior over the standard behavior without the recommender system. So along the road, we rediscovered some already known notions related to our analysis. So PageRank and Shapley values. So the first came out related to the overall influence of a user U. It turns out that the overall influence of a single user is his PageRank, actually. PageRank computing in the graph given by G, the graph of social relations between the users. And this makes sense, right? So the more a user is listened to by his direct neighbors, and the more the neighbors of neighbors listen to them and so on, the more a user is influential in the overall market. The second notion that of Shapley values comes out, so it was proposed times ago as a measure of how much a participation of a user in a game is worth. So the game is basically the following. The user either chooses to participate in the recommending process as described, or it sets his personal preference for the product to 0. Oh, okay. Mm-hmm. Yeah. Yeah, right. Yeah. Yeah, yeah, exactly. Yeah, yeah, yeah. Yeah. The thing is that here you're not sure that the thing, so once it converges, then it is clear that actually the result is a generalization of PageRank and cat centrality of both. You can see, but in a standard simplified scenario, they become the same thing. All right, so we rediscovered that the Shapley value, so a measure of how much I should pay a user for him participating into the process of the recommender system, is exactly equal to his influence time, his personal preference towards the product. This is what the results tell us. So there is a kind of nice connection with game theory that is worth probably exploring more in depth. All right, so after pinning down our theoretical part, we went through a set of experiments to see if real networks actually favor the distortion of markets or not. So what we do, we take real-world social graphs and we put all the rest artificially on top of it. So we imagine a market with just 2 products. One of them we are observing, the other is a kind of aggregate for all the possible products in the market. We don't care about them. We assign random personal preferences to each user in the network. Then we set a recommender, a probability of listening to the recommendation to 20%, which is a quite high value if you look at the existing literature, to the purpose of boosting the effects of the recommender system. We want to see in a very conservative case if the recommender can indeed steer the market a lot of, or or not. We set just uniform arc weights, so people, when listening to recommendation, pick a neighbor uniformly at random. The purchasing rates are uniform, so everybody purchases the same number of items on average per unit of time. And we use two scenarios for our weight of history. So in one of them, users just suggest one at random of the items they have bought so far from the starting of time. And on the other, they only remember the most recent product. So they have a very short memory. They only suggest the last trending items they were happy with. All right, so this is the convergence of the system. So we simulated this system on all the networks we had, and the behavior of the system in time with the number of purchases per user behaves as expected. So this is the L infinity norm, so the distance between the distribution vector of the sales and the predicted distribution vector by theory of the sales at the limit. So it goes to zero quite rapidly with T on all the networks. So the convergence that before was in expectation, now here holds even, so to say, with high probability, right? So this is for the long memory scenario. For the short memory scenario, where people recommend only from the last 10 items bought, well, there is much more noise. The system converges fast towards the limit at the beginning, but then settles kind of distant from the predicted distribution. But this is just normal. So the distribution, the convergence is in expectation. But if users are recommending only from their 10 last purchases, then of course each time one of these purchases changes, the user recommends something that is 10% different from what he saw one purchases before, right? So there is a kind of high churn between the last 10 purchases that makes the system behave like that. But it is quite stable in any case. So this just confirms that things go as we expect. And the next thing is to measure market distortion thanks to the, according to the measures we defined before. It turns out that on all graphs, the market distortion is very low. So, so delta, the measure of how much the product sales change, is always in the range 1 plus minus this very tiny quantity. So it seems like that the real-world networks don't favor the distortion of the market if you put a recommender system of this kind over them. We find only two ways to distort the market, and the first one is to explicitly plant an oligarchy of a very few very powerful users that recommend constantly to all others without being affected by them. And the second, this is the first way, and the second way was to use a strong nonlinear weighting of history. For example, increasing the probability that I recommend a product from my history to a superlinear quantity in his super proportionally to the amount of times it appears in my purchasing history, right? So this strongly reinforces with a strong feedback the item that just by chance is taking slightly over in my purchasing history. Finally, we look at the influencers in those networks. So a very interesting thing is plotting out who are the people that are the ones most able to influence people in the market. And here what you see is the maximum over all users of the overall influence of user in the market on the various networks. On the top chart, this is plotted just according to definition. So it's the fraction of the overall sales that are due to that user. All right. It is more meaningful to look at the second one, which is in terms of equivalent users. So this is the first multiplied by the size of the network, so the number of users in the network, and tells you how much average users this powerful user is equivalent to, right? So for example, on the Twitter graph by the Laboratory of Web Algorithms in Milan, the most powerful user is as powerful as something like 100,000 users altogether. So it's like 100,000 users are constantly buying what he commands, right? In any case, in terms of normalized influence, it's still pretty small. So the graph is quite huge in that case. So still we have robustness to market distortion. All right. Just one slide more. So we proposed, we took a first step towards understanding the market effects of recommender systems. We developed a model that we believe to be simple but fairly general to model a variety of scenarios. We gave a closed form for the steady state behavior of the market, for the distortion of the market, for the influence of the users acting in the market. And the experiments suggest that real social networks are kind of robust to distortion effects. There are many open direction next, but one I want to point out is the analysis of specific recommenders. For example, collaborative filtering has some peculiarities that might be worth to explore, since it is one of the most prominent kind of recommender system proposed in the literature. Another thing will be a dynamic market with users entering and leaving, so no market is constant. Every network here is strongly evolving in time, is shrinking, is growing, relationships are changing, the graph are changing, and so on. And another final direction are games where users might choose what to recommend or not to recommend according to some incentive, right? So I am a centralized system that can pay users in some way to encourage them to recommend my product. So the question is, what is the value of a user that chooses to recommend my product instead of another one? All right, thanks for listening.
Questions? So one of the uses of the model was to put edges in the graph to connect users who are similar, and then have the recommendation system operate like an Amazon-style thing. Mm-hmm. In that case, what really happens, I guess, in practice, is that the weighted combination of the recommendations that would come from all the related users are computed, and then the top ones are actually shown. And so this introduces a nonlinearity that seems as though it might have the potential to change the dynamics to a winner-take-all, in which few items could actually become a growing fraction of the set. Any thoughts or study of what happens when you no longer have the linear model?
Yeah, this is an extremely good question. So, yeah, two things. Well, there was a preliminary study of a system exactly like that. So the system is actually pretty simple. You just recommend always the top item, right? So there is a very simple threshold effect over which you start recommending always that, and that takes over not the whole market, but the recommendation, the market driven by the recommendations. A related thing is nonlinear, let's say, approaching that kind of threshold function, a threshold recommendation function with nonlinear probability. So we did some experiments on that, pushing up the nonlinearity. So you recommend a product with probability proportional to his share in the purchasing history raised to the sum power. So starting from 3, 4, you experience essentially all the same behavior, even if you push to infinity, basically, right? Even in those cases, so if you push really strongly and you emphasize the effect of the recommender increasing the alpha, then the market starts to be driven towards the recommendations. But otherwise, on that kind of networks, it remains very, very stable. So you have to take some of a kind of unreasonable parameters assumption. Okay. But that are close to what you say is not exactly what you say. It might be that in that case, distortion might occur.
Yeah.
Sebastiano, yeah.
So there's some work of Friedkin in the early 90s on consensus, which mathematically, I don't know if you are familiar with that. So basically they have this influence matrix and then they get to the matrix L to measure influence. Do you know what are the things in common with the consensus model?
Yeah, thanks for the question. Yeah, so that work, so it is different in the sense that well, that is an opinion formation, right? Work is about opinion formation. And they assume, let's say the algebraic form is the same. If you look at the formula, it appears like the same thing. But there are some differences. So first of all, they assume a deterministic system. So it's not a stochastic system at all. It's just a sequence of rounds where you recompute the power and the thing essentially, it's like an eigenvalue you're pumping, like it's essentially that kind of thing. So this adds many degrees of freedom. You have a graph, you have arbitrary weights on graph, you have arbitrary purchasing rates for users, you can personalize on the probability of listening by each user, you have the weight of history that can be modulated in any way you want. So that's related algebraically, in some way, high level, but there are a bunch of differences also.
Okay, so we have a final question here. It might be in the meanwhile we set up for the other machine.
There seem to be two different recommendation systems that are mixed up here. So one of them is you have a network like Facebook where you have fixed set of neighbors and you're influenced by them. And then you have the recommendation system from, say, Amazon or Yelp, which aggregate over the whole population. And so every time your recommendation is aggregation of everyone and related to the particular thing you're looking for. Do you see different, so for example, it doesn't influence, there's no influence there of the network because you actually aggregate on the whole population. So do you see different performance in these two systems?
Well, so initially we started with an idea like aggregate over all your neighbors and then take a decision. But then when we switched to recommending with probability proportional to the number of appearances of a product in the history, we just split by neighbor because choosing at random of the neighbor from the neighbors will end up essentially the same thing and gives the power to choose weights on the neighbors, which can be, for example, similarity weights, right? So I agree they are different. I don't know what happens exactly in that case. We haven't studied that yet. But we started from an idea like that and then switch it to this one. There are similarities and differences. But if you have an idea of what might happen.
Okay, let's thank again the speaker.